So, lesson 3, we're going to learn about something called Hess's Law. So, here we can see the understandings and the applications and skills. So, in Hess's Law, we know that energy is never created nor destroyed. Therefore, no matter how you get from one substance to another substance, the same amount of energy is absorbed or released. The change in enthalpy is what we call a state function. That means it is a property whose value does not depend on the path taken to reach that specific value. In contrast, functions that depend on the path from two values are called path functions. Both path and state functions are often encountered in thermodynamics. So, what this is basically saying is no matter how we get to our end result, it does not matter. So let's take a look at Hess's law in action. Okay, here we have an example of a reaction where we can take three elements, carbon, hydrogen, and oxygen, and we can combine them to create two products in one reaction, and then do a second reaction to get our final products. Or we can take those original three elements and do a reaction to get our final products. So as you can see, there are two routes, two paths to get to our final answer. Okay, if we consider the clockwise route, which is in red, if we follow that along, we have two reactions, so two enthalpies, and we can add those together, the negative 277 and negative 1367, to get a total of negative 1644 kilojoules per mole. If we consider the anti-clockwise route, which is in blue, this says its enthalpy is negative 1646 kilojoules per mole. So, given the uncertainty of the experimental values, we can conclude that our enthalpy delta H3 is equal to the sum of enthalpies 1 and 2, delta H1 and delta H2 added together. Okay, so this is an example. It doesn't matter which route we take or which path, you get the same answer at the end. So, Hess's law, as a definition, states that the enthalpy change for any chemical reaction is independent of the route provided, the starting conditions, and final conditions, and the reactants and products are the same. The steps in an enthalpy cycle may be hypothetical and may refer to reactions that do not actually take place. The only requirement is that the individual chemical reactions in the sequence must balance. Okay, this is a really important point. Sometimes we're going to be considering reactions that don't actually exist or can't or won't happen for one reason or another, but we can consider them. So when performing calculations using Hess's law, it is like a puzzle where you need all the intermediate steps to cancel out in order to get from your reactants to the products. So let's talk about what you would see and how you would actually use Hess's law. So here's an example. You're given two reactions, and you're also given two enthalpies. What you are asked is to calculate the standard enthalpy change for this third reaction, which is what we're trying to figure out. Okay? So we have two reactions, 1 and 2, we're trying to get to this third one. So consider this as our final answer we want to get. What we need to do is take these two equations and these two enthalpies, and we need to manipulate them so that the reactants and products are equal to what we have here. By manipulating them, we will get some reactants and some products to cancel out, leaving us with our final answer. Okay, so let's consider this. So, reaction 1 starts from the required starting point. Okay, well, reaction 1 starts with sulfur, which is a reactant, and sulfur is a reactant for our final product. Okay, this is good. We also have oxygen, O2, in both of our reactants. Okay, we do not need to do anything with equation 1 for right now. Okay, we have 1s, 1s. We have 1.5 oxygens here and only 1 in our final answer, what we're looking for. So we will have to take care of that. The other thing to consider is we have an SO3 in this equation 1, but it's not present in our answer. So let's go on. Reaction 2 relates sulfur trioxide to sulfur dioxide. To finish with the required product, we reverse the chemical change and the sign of the enthalpy change. Okay? So what this means is we're now comparing sulfur dioxide and sulfur trioxide. And if you look at our reaction, what we want, sulfur dioxide is a product. But in reaction number 2, it is given as a reactant. So what we can do is we can flip the equation, right? We make sulfur trioxide a reactant and make our reactants now our product. And by flipping the equation, we also flip the sign of our enthalpy change. So if it was negative before, by flipping the equation, you make it positive, and vice versa. Now what we can do is take those two reactions, number 1 and 2, remember that we flipped this second equation, and we can add them up, seeing what is on the left-hand side of the arrow and seeing what is on the right-hand side. If there are things that are on both sides, we cancel them out. So we can see we have a sulfur trioxide molecule on both sides, which are canceled, and we have 1.5 O2 molecules on the left and only a half of an oxygen molecule on the right, so we can cancel out a half. So we simplify and we ultimately get the final reaction that we want, which is exactly what we were looking for. To get the overall enthalpy change, we take the negative 395 and we're going to add 98, because remember, we flipped the equation, so we flipped the sign. You add that together and you get an enthalpy change of negative 297 kilojoules. So most likely what's going to happen is you're going to be given some equations and you're going to have to manipulate them. You could flip them, or as you'll see later on, you might have to multiply by 2, 3, etc. So you must do whatever you can to those equations to get your final answer. Okay, let's look at some practice questions. So number 16 says that the diagram illustrates the enthalpy changes of a set of reactions. Okay, so we have 4 letters, P, Q, R, and S, and we have 3 different enthalpy changes going on. And we want to know which of the following statements are correct. Okay, so number 1 says going from P to S is negative 10 kilojoules. Number 2 says R to Q is positive 90 kilojoules. And number 3 says P to R is positive 20. Okay, so we do not know right off the bat what P to R is. Okay? That is totally blank, but we know the other three. So let's consider what we're given and try and figure out which of these statements is true. Okay? I want you to think about it first. Okay, well let's start with our P to S. So it says P to S is negative 10 kilojoules. Okay? Well, to get from P to S, you have two routes. Okay? We don't know what this is, but we do know what P to Q and then Q to S is. So if we're going to go this direction, we can add the positive 50 to the negative 60, which gets us to negative 10. So P to S is negative 10. Right? Then it says R to Q is positive 90. Okay, well, again, we can't go up from R because we don't know what P to R is yet. But if we go R to Q, let's follow the arrows. Okay, so we're going to take our positive 30, and then we have S to Q. Going from Q to S is negative 60, but if we go the opposite way and we flip the arrow, just like we flipped the equation before, we flip the sign of delta H. So if we flip this arrow, delta H now becomes positive 90. So positive 30 plus positive 90 gets us, or positive 60 gets us positive 90. So we can check 1 off, we can check 2 off. Okay, now let's see if the third example is correct. It says P to R is positive 20. Okay, so this is where we're trying to figure out what P to R is. Okay, well, we know that P to S is negative 10, right? We figured that out going up top. Well, if this way is negative 10, then that means going P to S down should also equal negative 10. Okay, it doesn't matter which path you take, they're going to be equal. Well, if this way is negative 10 and R to S is positive 30, then this value, positive 30, plus whatever this is, should be equal to negative 10. That would make P to R have to be negative 40. It says P to R is positive 20. So number 3 is not correct, which means that letter A, only 1 and 2, those statements are correct. All right, here we have a bunch of practice questions using different equations. Okay, my recommendation for solving these problems, okay, is to look at your reactants and your products for the reaction you're looking for and try to get the reactants and products the same from the 2 or 3 equations that you have enthalpy values for. And from that, then you either flip equations to try and get the products to match up and cancel out. And then remember, if you flip an equation, you have to flip the sign of the enthalpy change. The other thing that you might have to do is multiply an equation by 2, 3, 4, whatever, to get the appropriate number of molecules of your reactant or product. If you have to multiply an equation by 2, then you also have to multiply the enthalpy change by 2. Okay, so you have a couple of practice questions here. Okay, let's look at 17. We'll go through a couple of these quick. All right, in 17, we want to get carbon added to oxygen to get carbon monoxide. Okay, so the first things that I see is carbon, which is graphite in its standard state, is given as a reactant. So we shouldn't have to manipulate this equation. And then looking at the second equation, carbon monoxide is a reactant in here, but we want it to be a product. So that means we're going to have to flip this second equation, which means if we flip the sign, we would get positive 283. As well, if we flip that equation, then we'll have a carbon dioxide on both sides, and that cancels out because we don't have any carbon dioxide in the reaction that we are trying to calculate. So we didn't do anything for the first equation. We flipped the second equation. That means that our answer should be negative 111 kilojoules. That's what you should have gotten. All right, we can take a look at number 18. Okay, we're trying to find the enthalpy change for that reaction, and we're given these two equations. Okay, again, look at your reactants, look at your products, see which equation you might have to flip. Okay, well, automatically, I can see that we have an NO on the left-hand side, on our reactant side, but in our equations, we don't have any NOs on the left. Here it is on the right. So what we're going to have to do is flip that first equation. And by doing that, we will then be able to get nitrogen molecules canceled out on both sides. And then we will also be able to cancel out one of the oxygen molecules. So the only thing we did here was flip the first equation. Okay, make the reactants products, switch them, make this positive 180.5 into negative 180.5, and you should have gotten negative 114.1 kilojoules. Here we go for number 19. All right, consider which reactants and products you have. Okay, well, I see I have a N2O4 in a product, and here it is in a product down below in the second equation, so that's good. I shouldn't have to manipulate that. Here I have an NO2 on the right-hand side in the products, but I need it to be on the left-hand side. The other thing to consider is that there's one NO2 in the products, but I need two of them in my reaction. So, not only do I need to flip this first equation, which would also make this negative 33.2, I need to multiply everything by 2. So, it's going to be negative 33.2 times 2 after I flip the equation and multiplied by 2. When I do that, I will also make it so that the nitrogen and oxygen molecules are equal on both sides and they cancel out. And after those changes, you should get negative 57.24 kilojoules per mole. All right, these are the types of questions that you are going to get where you have to apply Hess's law. It doesn't matter which equations you're given, which route you take. You just have to cancel out, manipulate equations to make everything work. All right, one last one that I want you to consider. The thermochemical equations for 3 related reactions are shown. All right, we're given the first two. We want to calculate what delta H3, what the enthalpy change for the third equation is. Okay, think about what you're given what you might have to do, okay, something to consider is the fact that you have two waters in the first two in the second equation here, but you only need one at the end. Okay, so what do you have to do in that case? All right, after you do all of your work, if you did it correctly, you should have gotten letter B, -3 kilojoules per mole.